Hi and welcome to this video. In this video, I want to talk about evoked potentials. Evoked potentials are also recorded in a very similar manner to EEG, right? They are recording the electrical activity of the brain, but instead of recording the electrical activity of the brain as such, we are recording potentials in response to certain stimulations. Okay, so you give a stimulation and you record the response of the brain immediately after the stimulation. Okay, so that's what evoked potentials are. And they help us to see different neural circuits and detect problems in different neural circuits, as we'll see as we go on. Now, if you are talking about, you could record evoked potentials from different parts of the brain, right? And depending on which part, what kind of stimulation you're giving, you will have to put the electrodes in different parts of the brain. So if you are doing visually evoked potentials, so you're giving a visual stimulus and recording a response to that, you will put your electrodes at the back of your head. Why would you do that? Because the part of the brain that is responsible for vision, the occipital lobe, is at the back of the head. Okay, so you put your electrodes in these places, in these spaces, and you record from those electrodes. If you look at fMRI data, which is kind of an MRI, but it shows the oxygen consumption of the neurons in the brain, and therefore we can detect which parts of the brain are active when we are doing certain activities. You can see that the occipital lobe is being activated when you provide visual stimulation to a person. So the visual stimulation can look like this checkerboard. And usually you give this checkerboard, and what you do is you switch the white and black patterns on this screen so that it's a dynamic kind of stimulus to the brain. And when you look at the fMRI data again, you can see that the back of the brain is getting lighted up. You can see here also the back of the brain, and the back of the side of the brain is getting lighted up when the stimulation is being provided. And what we want to do is now record EEG in response to this stimulus. And if you record EEG, you would get something like this, right? There doesn't seem to be any proper pattern. So this is where the stimulation is provided, and you can see, well, there may be a pattern, maybe not, don't know. Okay. But what you do is you do something called ensemble averaging. That is, you take a lot of stimulus and the EEG corresponding to that stimulus, and then you average them. We'll talk about this in just a moment. So when you take these ensemble averages, you get this nice shape so that you have kind of lost all the noise and you're just keeping the shape that is in response to the stimulation. And based on this response, we know that if your neurological system is working well, 100 milliseconds after the stimulus, you should get a peak. 70 milliseconds after the stimulus, you should get a negative peak, and there's a second negative peak at 140 milliseconds. And looking at that for different people can kind of tell you whether your visual system is working well or not. You can have sensory evoked potentials. So instead of giving visual stimulus, you could give sensory stimulus and then look at the sensory system to the brain to see whether it is working well. So there are various ways of doing it, right? So you could stimulate, for example, the median nerve, the right median nerve here, and you stimulate this, and then the signal then travels all the way through the median nerve into the spinal cord, through the spinal cord into the brain, where we have electrodes here, and we are recording from these electrodes, and you are expecting to see these shapes. Depending on which electrodes that you're recording from, you get different kinds of shapes. Similarly, you could also do a tibial nerve stimulation, and then you get slightly different shapes on the different uh, on different electrodes that you're recording the EEG from. So how do we actually do these recordings? We do what is called ensemble averaging. Okay, now what do I mean by that? Now take a look at this. So here's a EEG signal, and you're recording, let's say, from the back of the head, from the occipital lobe, and you have some electrodes on there, and you give the visual stimulus at this point, wherever the arrows are, okay, at 1, 2, 3, 4, 5. And what you do is you give the stimulus and you're recording the EEG, and after some time you give another stimulus and then you again record EEG, give a stimulus, again record EEG, give a stimulus, again record EEG, and you do that quite a number of times. Then what you do is you take this you take the EEG signal around the stimulus. So here's what we have done, right? Kind of orient the signal. So divide this signal into parts and kind of orient them. Bring, let's say, this part of the EEG down, this part of the EEG here, this part of the EEG here, and average them out. Now, when you do the averaging, what is going to happen? The noise and signals that are really not related to the stimulus are going to get averaged out, while if there is a response to the stimulus, that's going to keep adding up, right? And that's how you get those nice evoked potentials that we saw previously. So for example, when you are just recording signals, you may get signals like this, okay? And there's no discernible shape here. But if you do ensemble averaging and you use 25, you get a signal like this. So you have reduced some of the noise, but still you can't see a very nice shape, isn't it? If you average 100 of these signals, then you are starting to see a shape here. Can you see that? And if you do 400, you get a very, very nice shape. And that kind of helps you to, that is your evoked potential, and you can use that to kind of measure and diagnose and figure out what is wrong with the neurological system. Right. Hopefully that helps.